topic was tensioning cables and the buckling of struts. So I'm talking about tension, so you better pay attention. Okay. So anyway, it's a major component in structural engineering. And so what you look at when you're studying bridges, which I looked at bridges specifically because that's what these are mainly used in, is strength, stiffness, and stability. And so it's examples of bridges that use cables and struts in their construction. So cables, it's a metal rope that are usually in tension, and there's many different types. So the wire rope, which is made up of many strands. Usually cables are made of many strands because it's more flexible. And so the wire rope would be the most flexible. The structural strand would be the most strong, not always the most strong, but it's cheaper to make because there's less little wires and it's strong. And then the full lock cable, it feels smooth on the outside and it's also denser. So that makes it strong as well. So basically, we all learned this in our physics class. Tension, because the object is not moving, has zero acceleration, then the net force is zero. And so the tension equals your weight, which is mass times gravity. And then if you look at cables that are at an angle, then you look at the x components and the y components separately. So the x components would equal each other and balance out, and then the y components would equal the weight pulling down, because as I said before, all the forces are in equilibrium. Okay, so even if you pull a cable really tight, there's still going to be a sag because of gravity, and so this is called the catenary sag. And so as you can see in the suspension bridge, it's the main cable that slopes down, so you have to take that into account. And so for struts is the supporting beam that's always under compression. And it's often found in bridges, but it can be found in other things such as airplanes and cars and buildings. And it's made up of a variety of materials like metal, wood, and stone. So as I think Clayton was talking about bending of beams, buckling is basically the same thing except you're putting force down on the lateral side. And so on the long side you're pulling it, or you're pushing it down, and then it buckles. So this is the equation. Oh, it didn't come out right. That's okay. For Euler's equation of the critical load, which is basically once you reach that load, then your beam will buckle. And so it uses Young's modulus, which is based on materials. And then this is calculating the critical stress, which is the force per unit area. And so you look at your slenderness ratio of the beam and the effective length ratio, which I'll talk about later, and also the radius of gyration. So if you have a smaller radius of gyration, then you have a smaller critical load. So this is the slenderness ratio. If you look at it, it's kind of like the proportion of the beam length to the width. And then as the slenderness ratio increases, then the amount of strength that it can hold decreases. And then the K, which is the effective length ratio, is based on the situation that it's in, like literally with the different points, fixed or pinned. And so that's an example of a buckled strut that was fixed on both ends. And then applications of this would be like struts are found in trusses. And so there's ties and struts. Ties are like beams, but they're beams under tension, and the struts are the beams under compression. And so they work together to make the structure that's strong enough to carry things across. And then another application would be the suspension bridge, such as the Golden Gate Bridge. And so the cables are under tension, and then the main towers are under compression. And you can see this is a cross-section of one of the cables, and it's so large because it has to carry so much tension. And so because the suspension bridges are strong, they can span a long distance, usually. So there's also this bridge. This is the cable-stayed bridge. And it's like a suspension bridge, but instead of a main cable going across, you have cables that are going directly to the deck. And so it is more stable because the cables are balanced on either side in tension. And it's also cheaper to make than suspension bridges, but it usually doesn't reach as long as a span. So if you're looking for long distances, then a suspension bridge is usually better. But cable-stayed bridges are good if you want to limit the amount of materials that you're using. And then I thought this was interesting too, the Michelward Bridge, which is an example of an underspan suspension bridge, where the cable is actually on the underneath side rather than on top. But even though it looks cool, it's actually less stable and can hold less load. So it's not as practical as using a suspension bridge or a cable-stayed bridge. And so the impact of these is that they're still looking at different materials to use that can make stronger bridges and stronger cables and struts. But usually those materials are more expensive because they use more rare metals and different mixes. And so they also are developing ways to improve bridges. Cool.
Sorry, okay.
Oh, sorry. I don't know how to use a Mac.
Okay.
PC nuts, I don't know how to Macintosh.
Apple products.
Teach me how to, right?
Teach me how to
Teach me how to operate.
Cool.
There you go. Inheritance pack.
Okay, so Jean-Miron de Alembert. He was the mathematician that I studied. He's a French mathematician, but he also studied a lot in physics. And so he was during the 18th century, and he actually was going to study philosophy, and he taught himself all this math. So we all know the ratio test from calculus. It's also called the D'Alembert criterion because he discovered it. And so you can look at the behavior of a series by seeing if it converges or diverges by using his ratio test. And he also found the equation for one-dimensional waves. And so he found this equation, which is based on partial derivatives, and Euler actually used this equation to find the equation for three-dimensional waves. And so the D'Alembert principle is based on Newton's third law, F equals ma, and D'Alembert said that F minus ma equals 0, and it may seem the same, but it's not the same, because he says that the forces are in equilibrium, and minus ma is actually the D'Alembert force, or called the initial force, or it's also called the frictional force, because it's just an imaginary force. You're looking at the problem from, instead of a dynamic perspective, but you're seeing it from a static perspective. So that's how D'Alembert changed the way that you see forces. And then the D'Alembert paradox is in fluid mechanics, and we actually learned about this yesterday, that in an inviscous and incompressible fluid, there should be no drag mathematically. But if you try this out in real life, there actually is drag in water and air, and so he discovered that. And then he also modeled the three-body problem, which is three objects in space and their gravitational pulls with each other. And so he rivaled with Alexis Carrel to find the solution, and they actually didn't find the equation, but they just worked on this problem against each other. And so D'Alembert was actually really into roulette, and he found this system or strategy because he believed in the balance of nature. And so if you lose a lot, then he thought you would win a lot later on. So he gambled. But this actually is not true because each event is independent of each other. So another thing D'Alembert worked on was encyclopedia with Diderot, which we all know it had everything from literature to economics to politics, but D'Alembert specifically edited the math and the science articles in the book, and this was widely read around at the time. Okay, so my scientist was Ernest Mach, who was a physicist at the turn of the 20th century, and he was a professor at the University of Prague, and he studied a lot in sound waves and also a little bit in optics. So the Mach bands is something he discovered. He couldn't really explain it, but he found that in this gradient, it looks like there's like a thin light band here, and it looks like there's a thin dark band there. But that's just actually just an optical illusion that's not really there, and it's because of retina filtering. And so one of the big things that Mach studied was sound waves. And so he looked at photographs that he took of the pressure waves that sound waves form, and he found that at different velocities, the sound waves look different, or if the objects go at different velocities. So the Mach number is object speed over the speed of sound. So for example, Mach 2 would be 2 times the speed of sound. And so he studied that and found that you can look at the angle of the object, and you can also calculate the object's speed that way. So subsonic is under the speed of sound, under Mach 1. So these are like the Cessna that we flew on, low speed planes. The air has equal density, and so it has no wave drag. Transonic is at the speed of sound, and it has more turbulence because of the shock waves formed by the areas of the plane that are going over the speed of sound. Supersonic is over the speed of sound, so you can see the sonic boom, which is formed because of the rapid change in pressure as the object goes past. And then hypersonic is many, many times over the speed of sound, sometimes up to like Mach 20, because it's usually formed from objects that are coming back into the atmosphere from space, and you can see it because it's going so fast that the air around it actually heats up because of the friction. And so that's an example of a satellite coming in. And so Mach diamonds is something that he also discovered. He couldn't really explain it, but it's actually because of the pressure difference from the exhaust and the atmospheric pressure, and so it forms waves, and then they coincide forming these Mach diamonds that you can observe. Then the Mach principle was actually based on D'Alembert's inertial force, that an object's inertia is because of its relationship with everything else in the universe is gravitational pull. So that's why an object has inertia. So it just changes the perspective. And then he also wrote this book, and it was saying that observations and experiments should be the basis of theories rather than mathematical analysis. And this is actually the opposite of what D'Alembert had been proposing. And so this theory was known as Machian physics. So the impacts of these people were very important. So for example, Mach is associated with speed, like the Mach bike in Mario Kart. And then gamblers like to justify themselves by using the D'Alembert theorem, even though it's not really that valid. Yeah, thank you.